Hello everyone, in this video we are going to understand the conversion of the galvanometer into an ammeter. Now galvanometer basically is an instrument that is used to detect very small currents in the circuits, and you cannot use it for higher value of current because the coil inside it will get burnt. Now if you want to measure anyhow higher currents with the help of the galvanometer, what can be done is the following. So first of all, let's understand that we have a resistance of 5 ohm which is connected with a 10 volts battery. So simply, if I write V is equal to I times of R, the single resistance will eat up the total voltage of the battery. So over here the potential difference is again 10 volts. So 10 volts is equal to 5 ohms times the current. So the current coming out of the battery will be 2 amperes, and the same current will go back inside the battery. Now if we wish to measure this electric current which is coming out of the battery, I'm going to place an ammeter because ammeter is always placed in series, and ammeter is an instrument that measures the electric current. Now suppose it has its own internal resistance as 5 ohm. Now the total resistance of the circuit will become 10 ohm, and the same 10 volts battery is fixed over here. Now in this particular case, if I apply the Ohm's law, 10 volts is equal to some current times 10 ohms, because since these two are in series, I'm going to get my answer as 1 ampere. So which means in this case, the current coming out of the battery and the current passing through the ammeter is 1 ampere. So this is going to read 1 ampere. So that means that this is a very bad ammeter. The ammeter has to have its own internal resistance as very negligible, because if this ammeter will have larger amount of resistance, that is going to add into this one, and smaller current will come out. Actually the current coming out of the battery was 2 ampere. In this case the battery is sending out 1 amperes of current due to the higher value of resistance of the ammeter. So ideally, in an ideal galvanometer, if this has a zero resistance, then this won't be counted and the current will be 2 amperes. So I should be saying that an ideal galvanometer should have 0 ohms of the resistance. Now practically this is not going to happen, because practically if you have an ammeter, it will have some amount of the resistance. This is the current I, which is the 2 ampere that is flowing across the external resistance, which is 5 ohm. Over here it is mentioned by R. So this capital I we wish to measure. Now this I current is going to flow through this resistance. Now we want to convert galvanometer into ammeter. So what am I going to do is, I'm going to connect a very small resistance which is known as shunt. Now this shunt is connected in parallel with the galvanometer. By the way, this galvanometer's own resistance is capital G. Now we know the parallel connections properties, that if two resistances are in parallel, the overall equivalent resistance will be even smaller than the smallest resistance. So here this is very small resistance. So equivalent resistance of this entire part, this part itself is the ammeter, will be extremely low. So let's assume that this current I splits up into two parts. Some current, let's say Ig, goes over here, and the remaining current I minus Ig goes in this direction. Okay. Now, if you look here, if you are looking at the galvanometer will show some reading like this. So here we have a galvanometer and it is written 20 milliamperes per division. That means this is first and second division. So here it should read 2 times 20. So that means 40 milliampere. So this itself is Ig. Correct. So Ig is some current that is passing through the galvanometer. Let's say it is 40 milliampere. Okay. Now we do know the fact that the potential difference between AB and CD would be the same as they are in parallel connection. So the potential difference across AB is same as the potential difference between CD. Potential difference between AB is Ig, the current times the resistance. So that is, I should be saying G times Ig. That is equal to, this is the resistance of the galvanometer, and here I minus Ig times S. Now let's open up the bracket. G times Ig. Now if I open up this bracket, I'll get I times S minus of Ig times of S, which I'm going to transfer it to that side. So I times S is equal to G plus of S times of Ig. Because when this goes over there, Ig is common. From here, I can say that I is equal to G plus S divided by S times of Ig. Now, if your I is over here, you are looking at some current over here, which is say 40 ampere, and I'm going to call this 40 ampere as Ig. So practically by looking inside the galvanometer, I know this part, I know this. Now, if I know the galvanometer's resistance and the shunt, if I know these two values, if I substitute all over here, this answer will be definitely more than 1, because see, this shunt is extremely small and this galvanometer plus shunt will be a larger resistance. So say for example, this part, this ratio is say for example 100, right? So this 100 times of whatever current that you are reading here, right, is your capital I. That's what it is. So I should be saying that this is 100 times of 40 milliampere. So that means your answer would be 4000 milliampere, which is equal to 4 amperes. So you can measure a larger current with the help of the galvanometer, very small deflections. So now what can I do is the following. Since I know the galvanometer resistance, if I know the shunt resistance as well, I know this ratio. So simply what am I going to do is, if the galvanometer shows the deflection of the second division, I'm simply going to cut this, because now this 40 milliampere in galvanometer corresponds to 4 ampere in the ammeter. So now I can call this as an ammeter, and this is how we can change the scale.